Now, my fractals document has got a few simple mathematical expressions in there. So let's now turn to some of the elementary aspects of typesetting mathematics and a few extra here. Leave until later on a lot more discussion. Let's share my screen again. So simple mathematics. Mathematics in LaTeX is treated in a completely different way, and it's invoked by specific environments to use. So the first sort of mathematics is simple expressions that are typeset in line with the body text. You should typeset the maths within the environment \parenthesis \n parenthesis. So it's not quite the classic begin-end, but that's because, you know, when you're doing mathematics, you've got a lot of mathematics and you don't want to type begin-end all the time, and it sort of gets in the way. Now, many of you will know and will have picked up a universal bad habit, and that is to use $signs on either side of mathematics. Okay, it works as long as it's used correctly. However, I recommend you avoid, because it generates incomprehensible error messages whenever you forget one or other of the $signs or put an extra $sign in that you didn't mean, right? The \parentheses are more robust to R errors, so they are better. Right, so let's have a look in the source. So, and on this page, we see some example mathematics. I've emphasized it by white space. Remember, white space is actually your most valuable way of emphasizing things. So this just typesets the letter D. Now, D is a mathematical symbol. It's the size of the object. And because it's a mathematical symbol, it needs to be typeset into a maths environment, as I've done it here. Don't just say size D without it being in maths. It's a maths thing, needs to be in the math environment. So the less trivial mathematical statements are to say things like n is 9 and n is 34. Let's typeset them and see where they are. Here we are. N is equal to 9 disks to cover the line segment. And then where's n is equal to 34? Oh, that's here. I've also got $signs in the code to typeset n is equal to L over D. And you can see they work perfectly fine. Just prefer to do the \parentheses versions. Now, I've also got here length L is n is equal to L over D. Note the L, it's a mathematical L, needs to be typeset in mathematics. So either the $signs or the \parentheses, just like the D was up here, which is there. Okay, and you can see it's a different D. Generally, we use italics for mathematics. And so if that was a Roman D, that would just be wrong. A Roman D is different to an italic D. They mean different things in math. There is actually a meaning for a Roman D in mathematics. It's in an international standard, it stands for the differential. So to call something of size Roman D, it's just plain wrong. Mostly your mathematics is italic. Not all of it, but I'll tell you more about that later. Different font, all, yep. Now, the other thing is, in a mathematics environment, blank characters are totally ignored. So, you know, all those blanks, totally irrelevant whether they're there or not. Typeset exactly the same thing like that. Right, nothing has changed. There it is, n is equal to 9. No difference whatsoever. Now, one of the simple things we need to do in mathematics is to have subscripts or superscripts. The caret symbol introduces a superscript. So d squared would be simply d caret 2, and d to the minus 1 would be d caret, and then the minus 1 with inside braces, because those braces group whatever is inside into one thing. So let's find caret. No. Oh, that's in the next source. No wonder I couldn't find it in that one. Yeah, there we go. So typeset that and go to the maths n proportional to d to the minus 1, and we get d to the minus 1 as promised by d caret minus 1 in braces. Similarly for subscripts, you go underscore character, and then if it's a simple symbol, you just put the symbol there. If it's a complex symbol that you want as a subscript, you enclose it in braces. Okay, so we've got a few more exponents, right? D to the minus 2, d squared, and so on. And d to the minus big D. Okay, similar for underscores. Now you notice a few other symbols in there. You can use proportional to by just backslash proportional and typeset that proportional to sign. You can typeset a times symbol as appears here. Big N is little n times d to the 0. So in short, LaTeX has a lot of symbols, and we'll discuss them more later, but such as times and proportional. It's got the entire Greek alphabet. It's got the fractal alphabet, got calligraphic symbols. It's got everything. We've discussed it later. So the other thing we do with mathematics is to display maths. So when mathematics is sufficiently complicated so that it should not appear in the body text in line, we display it. And there's two ways to do that which are different, but these are different here. There's backslash bracket, and that will display it, the maths, that's fine. Or backslash begin equation, backslash end equation will display the mathematics and also typeset an equation number. Let's see that. Here it is. Let's typeset and go to it. Okay, so this was 4a divided by pi d squared, and I decided for some reason that that was important enough to display and stand out. And there it is. And you see it's done by backslash bracket environment. And the result is it's centered with a little bit of space around it, so you can clearly see the maths. Now down here is a mathematical statement which could have been in line, but it's important enough that to be displayed and numbered. There's the number for referencing. So how do we get that? Command click. We put it in the equation environment in proportional to d to the minus d. And the equation environment gives the number. and I'll put in a second equation that happens to be a copy of the first, but you see the numbers changed automatically in sequence. LaTeX does all the numbering for you. Okay. We also saw the frac command for typesetting fractions. It's got two arguments. The first argument is the numerator, often in braces, but doesn't have to be if it's a simple symbol. And the second argument is the denominator, and usually that's in braces, but if it's a simple symbol, you don't need the braces. So that's in LaTeX. For us mathematicians who generate web pages, you can also use LaTeX to typeset maths in web pages in exactly the same way. It allows you to include mathematics in your web page source by typesetting it in LaTeX within backslash parentheses or backslash brackets. So, for example, one of the classic identities in mathematics is that EDI pi on 2 is equal to I via cosines and sines. We can get that typeset in a web page using just this code in your HTML or PHP source so that it appears like this. Beautifully typeset, much better typeset than any other way in web pages. And this is done by invoking MathJax. And what you need to do to get MathJax to operate on your pages is to include in your page this magic little recipe. And then whenever your web page is loaded, MathJax is asked to scan the page for mathematics to typeset using the LaTeX engine, and it does. Beautiful. Okay, so what else do we do in mathematics? Well, we do theorems from time to time, depending. So the best thing for theorems is to use what the American Mathematics Society provides. So use package AMS theorem. And then the environment that LaTeX provides you to generate theorems can be invoked. So what you do if you're going to use a theorem in your work is you say backslash new theorem, then the theorem environment name, and then how it's going to be typeset. It's going to be typeset with its header theorem with a capital T. New theorem, corollary, and how it's going to be typeset. Its title is corollary with capital C. Then I recommend you put in brackets, so it's an optional argument, theorem. What this does is it means that the corollary will use the same counter as the theorem. So this means the aim is to have just one counter through your document, and that counter counts the theorems, the corollaries, the lemmas, the definitions, all as one sort of thing, one theorem-y thing. And this makes it a lot easier to navigate. If you're looking for, say, corollary 3, and you've got to theorem 2, you know corollary 3 is going to follow. If you don't do this numbering, if your theorems and your corollaries are numbered separately, you've only, you've got corollary 1, 2, 3, 4, etc., and theorem 1, 2, 3, 4, and they're all intermingled. You've got no idea where corollary theorem 3 is when you find theorem 2, corollary 3. Okay. Keep it simple and just have one numbering stream, and that's what this square brackets theorem does. Same for lemma, same for definitions, and anything else that you might want. Assumptions, conjectures, propositions, and so on. Thereafter, as we'll discuss more later, you just include your theorem within begin theorem, end theorem. You include your corollary within begin corollary, end corollary, etc. They're all typeset well, they're appropriately numbered, and so on. There is a proof environment that comes from the AMS theorem package. Because they generate numbers, we use those numbers for cross-referencing, and that'll be described in the next section. These theorems, corollaries, lemmas, and definitions, they can all have an optional argument, which is such as begin definition, end definition, and the optional argument is this square brackets and a little bit of text, and that allows you to provide, some sort of name to that definition. So this one is going to be about right-angled triangles, whatever it is. Might be a squared plus b squared equals c squared. Okay, so that's about enough maths for now. So we'll stop and before the last section of this.